Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1504, count submatrices with all ones. This problem challenges us to count all possible submatrices in a binary matrix that consist entirely of ones. Stick around as we break down the solution step by step and explore key approaches to solve it effectively. We are tasked with counting the number of submatrices in a binary matrix, where all the elements in the submatrix are 1s. A binary matrix is essentially a two-dimensional grid where each cell contains either a 0 or a 1. A submatrix is defined as any rectangular section of this grid, formed by selecting contiguous rows and columns. Our goal is to find every possible submatrix that contains only one S and count them. For the input, we will be given the binary matrix mat, and the output will be a single integer representing the total number of such submatrices. This problem challenges us to consider all possible combinations of rows and columns within the given matrix and check which ones satisfy the condition of containing only one S. For the first example, we have a 3 by 3 binary matrix. The output for this input is 13, which is the total count of submatrices that contain only one S. To understand this, let's break it down. There are 6 single-element submatrices containing 1 for each one in the matrix. Then, we have 4 2 by 1 submatrices, which are formed by vertical pairs of 1s in the first and second columns. Additionally, there are 2 1 by 2 submatrices, formed by horizontal pairs of 1s in the second and third rows. Finally, there is 1 2 by 2 submatrix, located in the bottom left corner of the matrix. When we add these together, we get a total of 13 submatrices containing only one S. In the second example, the matrix is slightly larger, and the output is 24. Let's break this down as well. The matrix contains 10 single-element submatrices, 1 for each one in the grid. There are 6 1 by 2 submatrices, which are formed by horizontal pairs of 1s. Next, there are 2 1 by 3 submatrices, formed by 3 horizontally adjacent 1s in the second row. For vertical submatrices, there are 4 2 by 1 submatrices, which are formed by pairs of 1s in the same column. Finally, there are 2 2 by 2 submatrices, each formed by a square of 4 1s in the grid. Adding all of these together gives us the total of 24 submatrices. This illustrates how the problem scales as the matrix grows, with larger combinations of rows and columns contributing to the count. When solving this problem, there are a few key edge cases to consider. First, if the matrix contains only 0s, the output will always be 0, since no submatrix can contain only one S. Conversely, if the matrix contains only one S, the output will be the sum of all possible submatrices in the matrix, which can be calculated mathematically. For matrices with a single row or column, the problem simplifies to counting consecutive sequences of 1s and their combinations. Finally, for large matrices, such as the maximum size of 150 by 150, the algorithm must remain efficient to handle the input within the time constraints. This means our approach needs to avoid brute force and leverage more optimized techniques to count submatrices effectively. To solve the problem of counting submatrices with all ones, we can explore several approaches, each with its own strengths and trade-offs. The brute force approach, while straightforward, involves iterating over all possible submatrices in the binary matrix. For every potential top left corner, we examine all possible bottom right corners and check if the elements within the defined submatrix are all ones. Although simple to understand, this method is computationally expensive, as it requires nested loops and leads to a time complexity of O, open parenthesis m times n close parenthesis cubed. This inefficiency makes it impractical for larger matrices. Alternatively, we can use an optimized solution based on histogram logic. The idea here is to treat each row of the matrix as forming part of a histogram, where the height of each column reflects the number of consecutive ones extending upwards from that row. This makes it easier to count submatrices efficiently, as the structure of the histogram allows us to relate the presence of ones in columns directly to valid submatrices. The first step in this approach is to construct a height array that captures these consecutive ones for each column. Once the height array has been constructed, we use it row by row to count the number of valid submatrices ending at each cell. Treating the height array as a histogram, we iterate through each column and calculate the contribution of that column to the total count of submatrices. By summing up these contributions across all rows and columns, we achieve an efficient solution. The time complexity of this approach is O(m*n), as it involves constructing the height array and processing the histogram for each row. This method avoids the redundant calculations present in brute force, providing a significant speedup. Another way to enhance this strategy is by incorporating a stack-based optimization, which is inspired by the largest rectangle in histogram problem. Here, we maintain a stack while processing each row's histogram, allowing us to quickly identify the nearest smaller heights on either side of a column. This reduces redundant computations when counting submatrices. While the overall time complexity remains O(m*n), the use of a stack can make the implementation more efficient for certain edge cases, though it also adds some complexity to the code. After considering the available methods, the optimized histogram approach stands out as the most suitable strategy due to its balance of simplicity and efficiency. By reducing the problem to a series of histogram calculations, this method avoids the inefficiencies of brute force while remaining straightforward to implement. Although the stack-based optimization can improve performance in some scenarios, the added implementation complexity does not yield a significant improvement in asymptotic runtime. The key insights that led to this choice include recognizing that the number of submatrices is directly tied to the count of consecutive ones in each column, and that a dynamic histogram updated row by row eliminates redundant calculations. This approach is well suited for competitive programming, as it runs in O(m*n) time, making it scalable for large inputs. While brute force may be easier to conceptualize, its impracticality for larger matrices reinforces the importance of the histogram-based solution as the optimal choice. In this problem, we are given a binary matrix consisting of only zeros and ones, and our objective is to count all possible submatrices where every cell contains a 1. For example, consider the matrix shown here. The total number of submatrices with all ones in this case is 24. To solve this efficiently, we will use a histogram-based dynamic programming approach. The first step in this process is to build a histogram representation from the matrix. Here, we treat each row of the matrix as a level in the histogram, which will help us efficiently calculate the number of submatrices with all ones. Let's explore this step in more detail next. To create the histogram representation, we calculate the height of each column for every row in the matrix. The height of a column represents the number of consecutive ones from the top up to the current row. If the matrix at position ij contains a 1, we update the height as the previous height plus 1. On the other hand, if the matrix at position ij contains a 0, we reset the height for that column to 0, as the streak of consecutive ones is broken. Let's look at an example with the given matrix. After processing the first row, the heights array becomes 1, 0, 1. After the second row, the heights array updates to 2, 1, 2. Finally, after the third row, the heights array is 3, 2, 3. With the histogram representation in place, the next step is to count the submatrices using these heights. To count the submatrices, we treat each row as the base of a histogram and calculate the number of submatrices that end at each column. For this, we use a monotonic stack to efficiently determine the nearest smaller height to the left and right of each column. By knowing these bounds, we can calculate how many submatrices can be formed with the current column as the rightmost column. For every column, we add this count to the total number of submatrices for the row. This process is repeated for all rows to ensure that every possible submatrix is considered. Once we have processed all rows, the final step is to aggregate these results and return the total count of submatrices containing all ones as the solution. To implement this algorithm, we rely on a few key data structures. First, the heights array keeps track of the height of ones at each column for the current row. Second, the monotonic stack is used to efficiently determine the nearest smaller heights to the left and right for each column. Finally, the input matrix itself remains unchanged throughout the computation. Analyzing the complexity of this approach, the time complexity is O(n*), where n is the number of rows and m is the number of columns. This is because the heights array is updated for each row, and the stack operations for each column are amortized to O(1). The space complexity is O(m), which accounts for the heights array and the stack used to process each row. Let's now walk through the example matrix to see this algorithm in action. Starting with the first row, the heights array is 1, 0, 1. Using these heights, the number of submatrices with all ones is 2, 1 from column 0 and 1 from column 2. Moving to the second row, the heights array becomes 2, 1, 2, and the submatrices formed are 5 in total, 2 from column 0, 1 from column 1, and 2 from column 2. Finally, in the third row, the heights array is 3, 2, 3, and the submatrices formed are 8, 3 from column 0, 2 from column 1, and 3 from column 2. Adding these counts, the total number of submatrices with all ones in the matrix is 15. This example demonstrates the efficiency and clarity of the histogram-based approach in solving the problem. This implementation solves the problem by leveraging a histogram-based dynamic programming approach. Step-by-step explanation. 1. Input dimensions and pre-computing heights asterisk. We start by determining the number of rows, and columns, cols, in the binary matrix. Using a nested loop, we calculate the height of consecutive ones for each column. This is stored in the height array, where height, ij, represents the number of consecutive ones ending at row I for column j. If the cell contains 0, the height is reset to 0. 2. Count submatrices row by row asterisk. For each row, we initialize a monotonic stack, to help calculate the contribution of submatrices from the current row. We also maintain a current_sum variable to keep track of the cumulative sum of submatrices ending at each column. 3. Monotonic stack logic asterisk. As we iterate over columns, we use the stack to maintain a decreasing sequence of heights. If the current height is smaller than the top of the stack, we pop elements to calculate the contribution of submatrices formed by the popped height. The cumulative count for the current column is calculated as the product of the height and the width, using the stack. The result is updated by adding current_sum, which represents all submatrices ending at column j for the current row. 4. Result calculation asterisk. The result variable accumulates the total number of submatrices with all ones for the entire matrix. Finally, we return the result. Complexity. This approach has a time complexity of O, rows asterisk cols, since each cell is processed once. The space complexity is O, cols, due to the stack and auxiliary arrays. Edge cases. The code handles edge cases like all zeros, returns 0, and single rows/columns efficiently. This efficient and concise solution ensures that all submatrices with all ones are counted accurately. Here, we begin by defining the function number submat, which will calculate the number of submatrices with all ones in the given 2D array mat. First, we determine the dimensions of the matrix by extracting the number of rows and columns. Next, we pre-compute the histogram heights for each column. This helps us efficiently count submatrices later. The height array stores these computed heights, where each value represents the number of consecutive ones ending at that cell in the column. To populate this array, we iterate over each column, and for every cell, if the value in the matrix is 1, we add 1 to the height of the cell directly above it, otherwise, we leave it as 0. This step essentially prepares us to treat each row as the base of a histogram, which allows us to efficiently calculate submatrices using the heights. After this pre-computation, we initialize the result variable to 0, which will store the total count of submatrices. Now, we process each row individually to count submatrices row by row, starting with an empty monotonic stack and setting current sum to 0. The stack will help us efficiently manage and calculate the cumulative sum of submatrices for each row, ensuring that we maintain a decreasing order of heights for optimal processing. When iterating through each column in the current row, we use the monotonic stack to maintain the order of heights. If the stack's top element has a height greater than or equal to the current height, we pop elements from the stack and adjust the current sum by subtracting the cumulative sum stored in the popped element. This ensures that we remove contributions of previous heights that are no longer valid. We then calculate the count for the current column by multiplying the current height with the width of the submatrices it can extend to. If the stack is empty, the width is 1, otherwise, it is determined by the relationship between the current height and the top stack element. The current sum is updated by adding this new count, and the current height and cumulative sum are pushed onto the stack as a new entry. Finally, we add current sum to the result, which aggregates the total count of submatrices for this row. By iterating through all rows and columns in this manner, we efficiently calculate the total number of submatrices with all ones, and the function returns this result at the end. Here, we start by analyzing a small matrix example. Our first step is to pre-compute the histogram heights for each cell in the matrix. The height at any given cell represents the number of consecutive ones above it, including itself. For instance, in the first row, the height values are straightforward. At 0, 0, the height is 1 because there's a single 1, while at 0, 1, the height is 0 because the cell contains a 0. Moving to row 2, the height at 1, 0 becomes 2 because there's a 1 in the current cell and another 1 directly above it. We continue this process for every cell, carefully accumulating heights where ones appear consecutively. By the end of this step, we have calculated the individual height values for each cell in the matrix. To summarize the pre-computation, the resulting height matrix is now visible. For instance, at cell 2, 2, the height becomes 3 because there are 3 consecutive ones in the column. With the height matrix prepared, we move to the second step, counting submatrices row by row. To do this efficiently, we use a monotonic stack to calculate the number of submatrices ending at each cell. Starting with row 0, at 0, 0, we push the height value 1 onto the stack, which contributes 1 submatrix. At 0, 1, since the height is 0, the stack is cleared, and we push the new value, but it doesn't add to the submatrix count. At 0, 2, pushing height 1 again contributes another submatrix, bringing the total to 2 for this row. In row 1, we repeat the process with the stack. At 1, 0, we push the height 2, which contributes 2 submatrices to the total. At 1, 1, the stack is adjusted as we push height 1, bringing the cumulative count to 7 submatrices. At 1, 2, pushing height 2 adds even more, resulting in a cumulative total of 12 submatrices for the first 2 rows. Finally, in row 2, we process the height starting with 2, 0, where the height is 0, so no submatrices are added. At 2, 1, pushing height 2 contributes 2 submatrices, and at 2, 2, pushing height 3 adds 3 more. This brings the overall result for this example to 19 submatrices. Next, we explore a single-row matrix example. Here, the histogram heights are identical to the original matrix because there's only one row. The height matrix is therefore 1, 1, 1. Using the monotonic stack, we count submatrices row by row. At 0, 0, we push the height 1, which contributes 1 submatrix. At 0, 1, pushing height 1 again adds 2 more submatrices, bringing the count to 4. At 0, 2, pushing height 1 adds 3 more, resulting in a total of 10 submatrices for this row. With no additional rows to process, the final output for this example is 10. Now, consider a single column matrix. The histogram heights for this example are straightforward, as each cell's height is simply the cumulative count of ones above it. The height matrix becomes 1, 2, 3. Using the monotonic stack, we process the rows one by one. For row 0, at 0, 0, pushing height 1 contributes 1 submatrix. In row 1, at 1, 0, pushing height 2 adds 2 more submatrices, bringing the total to 3. Finally, in row 2, at 2, 0, pushing height 3 adds 3 additional submatrices, resulting in a total of 6 submatrices for this example. With the row-by-row calculation complete, the final output for the single-column matrix example is 6 submatrices. This concludes the walkthrough of the different examples, each illustrating how to use the pre-computed height matrix and the monotonic stack to efficiently count submatrices with all ones in a given binary matrix. In this problem, we need to calculate the number of submatrices that consist entirely of ones. To achieve this efficiently, the solution is divided into 2 main steps. First, we pre-compute the histogram heights for each cell. For every cell in the matrix, we determine how many consecutive ones extend vertically above it. This is done by iterating through all rows and columns, visiting each cell exactly once. Consequently, this step has a time complexity of O, rows * calls. Next, we count the submatrices row by row. For each row, we use a monotonic stack to efficiently compute the number of submatrices ending at that row. Within each row, we process all columns, and in the worst case, each column is pushed and popped from the stack once. This results in O calls operations for the row, and across all rows, the time complexity becomes O, rows asterisk cols. Together, these two phases ensure that every cell in operation is handled efficiently, avoiding redundant computations. Now, when we combine the time complexities of both steps, we get a total time complexity of O, rows asterisk cols, plus O, rows asterisk cols, which simplifies to O, rows asterisk cols. This is a significant improvement over a brute force approach, where enumerating all possible submatrices and checking each one would require O, rows caret 2 asterisk cols caret 2. Next, let's analyze the space complexity. During the pre-computation step, we store the histogram heights in an auxiliary array with the same dimensions as the input matrix, requiring O, rows asterisk cols, space. When counting submatrices row by row, the monotonic stack is used to store column indices and heights. In the worst case, the stack can hold all columns of a single row, which requires O, cols, space. Adding these together, the total auxiliary space complexity becomes O, rows asterisk cols, for the height array plus O, cols, for the stack, which simplifies to O, rows asterisk cols. This ensures that our solution not only runs efficiently but also optimally uses space. To fully appreciate the efficiency of this approach, let's compare it to a brute force or naive solution. A brute force method would enumerate all possible submatrices and check if each one contains only ones. This approach has a time complexity of O, rows caret 2 asterisk cols caret 2, as the number of submatrices grows quadratically with the dimensions of the matrix, and checking each one is equally expensive. However, it requires no additional space, so the space complexity is O, 1. By contrast, the optimized solution we've discussed leverages the histogram representation and monotonic stacks to reduce the time complexity to O, rows asterisk cols, which is linear with respect to the total number of elements in the matrix. The space complexity is O, rows asterisk cols, dominated by the storage of the height array. Whether in the best, average, or worst case, the time complexity remains O, rows asterisk cols, because each cell is processed exactly once during histogram computation and again during submatrix counting. Similarly, the space complexity consistently remains O, rows asterisk cols. The mathematical justification for this is straightforward: each cell and column is processed a fixed number of times, resulting in an efficient and scalable solution, even for larger matrices. When working with this problem, there are a few common mistakes that can trip you up. First, failing to correctly initialize or update prefix arrays is a frequent error. Since prefix arrays are crucial for optimizing submatrix computations, any mistake here can lead to invalid partial sums or dimensions, which ultimately produce incorrect results. Another common mistake is double counting submatrices. This happens when the traversal logic or conditions aren't set up properly, leading to some submatrices being counted more than once. The result is an inflated total count, so it's important to set clear conditions for distinguishing valid submatrices. Lastly, misunderstanding matrix boundaries can cause issues. When calculating prefix sums or iterating through the matrix, accessing elements outside the matrix bounds can lead to runtime errors or incorrect values, both of which will derail your solution. Paying close attention to boundary conditions is essential to avoid these pitfalls. In addition to those mistakes, there are two more critical areas to watch out for. Overlooking edge cases is a common issue that can lead to bugs or performance problems. For instance, matrices that contain all zeros, single rows or columns, or extremely large dimensions behave differently and need to be explicitly accounted for in your solution. Ignoring these cases often results in unexpected failures during testing. Another major mistake is relying on an inefficient brute force implementation. While a naive O, n to the power of 4, approach might seem straightforward, it becomes impractical for larger matrices and will likely exceed time limits in competitive scenarios or interviews. Always seek opportunities to optimize beyond brute force to ensure your solution is efficient and scalable. From an interview perspective, this problem is a great way to showcase key skills. One of the most important aspects is pattern recognition, being able to identify how brute force computations can be optimized using techniques like prefix sums, stacks, or dynamic programming. It's about spotting redundant calculations and eliminating them systematically. Another critical skill is optimization thinking. You can start by explaining a brute force solution to demonstrate your understanding of the problem, then transition into how optimizations like pre-computed data structures, such as histograms or prefix sums, can save time. Be prepared to discuss trade-offs between time and space complexity. For instance, while a histogram-based approach is efficient, it requires additional space for arrays. Handling edge cases is another area where you can shine. Discuss how you would handle matrices with no ones, all ones, or extreme dimensions. Lastly, strong communication skills are key. Walk your interviewer through your thought process clearly, explaining each optimization step and why it's necessary. This problem also has strong connections to other well-known problems, which can help you build a broader understanding of matrix-based techniques. For example, LeetCode number 85, maximal rectangle, is similar in that it also requires optimizing over submatrices in a binary grid. LeetCode number 221, maximal square, is another related problem, but it focuses specifically on finding the largest square of ones in a binary matrix. LeetCode number 304, range sum query 2D immutable, emphasizes the use of prefix sums to optimize 2D range queries, making it a useful reference for understanding prefix sum techniques. Finally, LeetCode number 84, largest rectangle in histogram, is particularly important because it's often used as a subroutine for solving problems involving binary matrices. Understanding these related problems will not only deepen your knowledge but also help you approach similar challenges with greater confidence. When solving this problem, it's helpful to understand the trade-offs associated with different approaches. The brute force method, while simple to implement, has a time complexity of n to the power of 4, and is only suitable for very small matrices. To improve efficiency, you can use prefix sum optimization, which reduces the time complexity to n cubed, but requires extra space for storing the prefix sum array. A more advanced technique is the histogram-based optimization, which transforms each row into a histogram and uses a stack to find the maximum rectangles. This approach achieves a time complexity of n squared, and is highly efficient, though it does involve additional logic to construct the histograms. Finally, dynamic programming offers another n squared solution by storing results for overlapping subproblems. However, it requires careful definition of state transitions. By mastering these approaches and understanding their pros and cons, you'll be well equipped to tackle not only this problem but also a wide range of similar challenges in matrix-based computations. Thank you for following along. We've tackled an interesting problem today, and I hope you've gained valuable insights into solving matrix-based challenges. Don't forget to practice similar problems to strengthen your understanding, and make sure to like and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!